Hello everybody and welcome to my first tutorial about GLSL, which stands for OpenGL Shading Language. And in this tutorial I don't really cover the shading language itself. I will rather just set up OpenGL so we can run shaders and try to explain a few things about shaders which could be important in the future. Okay, so before I go into the actual programming, first of all I want to clarify a few things, like what is the fixed people-in or fixed graphical people-in. In OpenGL. Basically you can imagine as a series of different operations in your graphics card. So whenever you define vertices, these vertex data will go into your video card and transformed according to the current translation, rotation, scaling, so on. And this is what the graphical people-in is, basically a series of operations which will be executed before the render actually happens. And with shaders you can actually replace the part of this people-in with the shader which you write, which is basically a source code, so you have much better control over what's going on than in fixed people-in. For example, if you wanted to use per fragment lighting, which mean that you apply the lighting calculation to every single pixel instead of every single vertex like the fixed people-in does, you can do that without shaders. So with shaders you can just basically replace part of this people-in, but because you replace it you will lose the fixed functionality there, so you will have no lighting calculations whenever you apply the shaders, you have no fog calculation, you have no other calculations. So in OpenGL there are three kind of basic shaders. This is the geometry shader, which I will not cover yet, but basically it can create vertices on the fly. So for example you pass 4 vertices into this shader and it will subdivide these vertices, and with it you can create much more realistic effects like, I don't know, water. But I will not cover this geometry shader yet. The other is the vertex shader. So the operation like go this first, here your data will go into the geometry shader, then the vertex shader. In the vertex shader, in the fixed functionality, the transformation happens, so you transform the vertices according to the current rotation, scaling, translation, and of course other things like lighting calculations are placed here in the fixed functionality, and some other functionality later on I will cover those as well. Then after it happens, something rasterization happens. Rasterization, maybe this, no, like this, I believe so. So it basically make your your 3D points into the 2D screen, and with it, after that, the fragment shader will come, which will basically tell what each pixel on the screen will have, what color will each pixel have on the screen. So the order is about that. You don't have to care about rasterization here. So this is the order, and we will not cover geometry in this tutorial. Okay, so I set up a little program. I use whatever we made in the FPS series, although don't worry if you haven't covered the FPS series. These files will be on the description, like the camera or the vector 3D class which we made. Okay, so if I run this program right now, I will see a triangle. It's just a very simple program. This is the white triangle. If I go with the camera, we can see that this is a 3D triangle and nothing basically, nothing special. Basically, I deleted the skybox and so on and so forth. So if I come here down into the display, you can see that I use the GL begin and GL end. And yes, I said that I will try to avoid decreased functionalities in OpenGL and use modern functionalities, but I think that it is just easier to see in this way and easier to just quickly modify something, although the shader will work not matter how you get those vertex data into it. It will work with display list, it will work vertex buffer object, and it will work with immediate mode as well. So I just drawn a triangle onto the screen at the -4 coordinate and call the camera functions. So that is basically, there is nothing more here to explain. So I believe we are ready to actually create the shaders. Actually, before we create the shaders, I will make the program which load the shaders, and then we create the shaders. So the shader is basically just a source code, like your C++ code. It's basically a text file, but of course you use the rules of the GLSL. By the way, the GLSL is a similar language to C++, but it's not C++, so this is a completely different language. So you will use the rules of this GLSL language whenever you create the actual shaders. And you can use a character literal like const char and create the shaders here. so like this, creating the shader right here. But actually I will not create the shader like this, because I will use separate files. I already created a vertex.vs and the fragment.frag file. The extension obviously doesn't matter, it just have to remember what is the fragment shader and what is the vertex shader, but as I said, it's just a text file, it's like any other file. So I use outside the file for that, because in that case, if we modify something in the vertex, in the shader, vertex shader or fragment shader, we don't necessarily have to recompile the program. We can just run it, since these files will load into the program in runtime, and it will allow much better formatting than a character literal. Okay, so let's create a simple function which will load the content of a file into a string. So nothing new in here, you should probably know that by now how to do that, but I will do that anyway. I have included the fstream and the string file as well, because fstream is needed obviously to open the file, and we will use a string to store every line of the file. Right, so this will be a void function, and I call it load file. First of all, I will give the file name to it, so const char file name, and second of all, I will give a string to it, which we will load into. So std string, a reference, and I just call it str. Right, so first of all, let's try to open it. So std stream, like input file stream, and just call it in, like input, and of course it's waiting for the file name. Now check if it is open. So if not in dot is underscore open. So if it is not open, then let's write out an error message and exit from this function. So std cout the file, and the file name right here cannot be opened. So if we mistype the file name, then we just write out a message, so we will know that it is mistyped and we should do something about that. And I just return out from this function. I will not care about this function anymore. Right, the next thing is to actually go through the file line by line and read each line to the string. So while not in.elf, while we are not in the end of the file, then actually I make a tmp variable right here, tmp, and make it 300, doesn't really matter. It's the maximum length of a line. Probably we will not make so long line that 300 character can store. So getLine, and this getLine in.getLine. This getLine function first waits the tmp and then 300, and it will read one line into this tmp except the new line character at the end of the line. And now str plus equal this tmp, and str plus equal the new line character. That was quite simple. So we just read in the line, and I manually put the new line character at the end, since getLine doesn't get the new line character, it just reads until it reaches the new line character. Right, and pretty much that was this function. So we will use this to load the fragment shader source code and the fragment vertex shader and the fragment shader source code. The next function will be actually load in a shader. So void and load shader. This load shader function will first of all waiting for the source code, which we have read in with the load file. So it's wait for an std string str. This is the source code. I could call it source as well. Maybe that make more sense. And the second is actually what mode do we want to load in. So is it a vertex shader? Is it a fragment shader? This is called GLSL, but probably because it's just a constant, this is just an enumeration, I can use just an integer right here. And what is it called? I will use unsigned integer, actually. Unsigned integer, and I call it mode. I haven't tested this out, probably I had a different kind of load function in the past, but I guess it should work. So first of all, we have to actually create a shader. Actually it will return an unsigned integer. Similarly than the textures, it has an identifier. Every shader has an identifier. Okay, so first of all we have to create a variable, and unsigned int, I call it id. This will be the identifier of the current shader. So id equals to gl create shader. GL create shader will wait a mode parameter, so what kind of shader it is. It can be GL vertex shader, like that, or it can be GL fragment shader. Oh, one thing I forgot to mention in the beginning of this tutorial, in Windows and maybe in Linux as well, because it doesn't compile for me, Actually, we have to use something called GLEE. This is a simple file written in C, which allows us to use extensions in OpenGL. Long story short, basically we need it to run the program. So if you just open up Google and write GLEE like this, GLEE, and probably you should write something like OpenGL at the end, because it will search for a series which called GLEE, but you will find it if you write OpenGL after that, and you can download it there, Windows and the Linux version as well. So after you have downloaded it, you can extract it, and there will be files in it like library files, which you can put into the obvious place. So wherever your compiler search for lib files, but you can actually just get the C file and the header file into the same directory as where we are. So I just put the header and the C++ file into this directory right here, and pretty much that's it. We will compile the C file with the rest of the files, and it should work. But in order to do that, we have to include the header file, and an important thing is to include before the GL header file. So include it right here. So include, and just call it glee.h, since this is the name of this header file. It is right here. I just placed it into the same folder. But as I said, you can get the header file put into your header file folder, and get the lib file and put it into the lib file folder. It will work as well. But it's easy to update in this way, since you just load the new C and header file and put it here, and it should work as well. Right. So and one other thing which I forget to mention is that you can only use shaders if you have OpenGL version 2.0 or greater. In order to test if we have a version like that, we can use a function called glGetString. So this will unsigned char and call it text, and this is equal to glGetString gl_version. This is getting the version of your OpenGL version, so you can actually just write this out. So std cout and text and std endline, and it will write out what kind of version do you have. So if we compile it now, what happened? Oh, we should make it a constant. Const unsigned char. And now if we compile it and run it, we can see what kind of version do we have. As you can see, I have a version 3.0.0 currently. It may help if you install the current drivers for your video card. Okay, so now it is greater than 2.0, so I can use shaders. And that's it. So this is just what should I mention before I actually start coding. Okay, so this GL create shader waiting for the mode. But actually I will not write here the mode, but I add it to the function mode. So I can just use this mode variable right here. Now that you have created the shader, you have to tell the shader basically what its source code. So if I go with C++ references, which I will do, the GL create shader is basically creating an empty file. Then the next function will actually fill up this file. So if I go with the C++ reference, you type in the source code. So the function is called GL shader source, and it's waiting for, and this has 4 parameters actually. The shader source function is actually very tricky because it doesn't waiting a string, which we use as like a string, like C++ string. Doesn't wait like a character literal, which we have. So doesn't wait like a const char C and something character literal right here, but actually waiting for a pointer to a pointer. So basically it's waiting for a matrix, and that's because it assumes that you may have stored the first line of the string. So the first line of the string in one line and one row in the matrix, and the second line of the shader in the next row of the string, so on. But actually this load file function load the string into one single line. So although we can actually assign this one single line, we don't have to make this string into separate lines. But there is a trick right here. So first of all, let me create first a const char, and then I call it shader source, or C source. I will call C source because it's a C style string, and this is equal to the source, which is our string object .c_str. If you have followed along, you probably know this function. It basically converts the C++ style string to a C style string. That's what it does. But now I can get the address of this pointer, and I can pass it to this function. So the first parameter of this function is actually the shader where you want to apply this source code. This shader is apparently the ID. So ID. The next is how many rows do you have in this matrix. I will only have one row, one single row, and the whole source code will be in this one row. So I will just write it 1 in the next parameter. Then the matrix itself, so I get the address of the C source. So as you can see, this is a pointer to a pointer right now. And the last parameter is actually how many characters does this string has. If it is a null terminated string, you can just write null right here, because it's a null terminated string, because CSTR will give a null terminated string. Right, so the next thing is to actually compile this shader. In order to compile the shader, we use the GL compile shader. Quite logical, and just pass what shader do you want to compile. We will compile the shader which is called this ID, which we have just created. So we compile the shader, and now we are pretty much ready with this function, although there is one big problem. We don't get the error messages, because GL compile shader will not write out error messages, compile error. By the way, there are no pre-compiled shaders in OpenGL or GLSL, so you have to compile it at runtime. So you would compile it. It can have advantages and disadvantages as well. Advantages that it may have in other cards, it may get more efficient, but the disadvantage that it takes time to compile a shader. So now that I clarified that, let's get the info, the error messages. We will use the function GL get shader info log. This is a long function, and basically it will get the compile status, which is basically the error, and it gets into a character literal. So I will make a char and error, and just make it 1,000 long. Probably we will not have so much error that we cannot fit into this variable. Okay, so the first parameter is what shader do you want to get the info, the error messages. We get the ID. The next parameter is how many characters at max do we want to get, which is 1,000. And the next is the return size, because it will return the size of how many characters was it which it gives back. But if we just pass null into here, then it basically just ignores this. By the way, it's obviously a pointer, so you get the pointer here, and it will fill up that pointer with how many characters do we have. And the last is the actual error. So error right here, which is our char pointer, which it will fill up with the error message. So I just write out std cout and write out compile status and a new line character maybe, and just write out this error right there and make a new line. Perfect. And we are pretty much ready with this function, although we don't really made a shader working yet, because before I go on to actual shader, it just load one shader. So in order to make this program working, we have to load two shaders, which it will compile these shaders. Then we have to link together these shaders, because a shader can have a lot of files, not just one vertex shader and one fragment shader, but it can have other files as well. Similarly, as in C++, you have a bunch of C++ and header file at the end of a bigger project. So, and we have to actually attach the shaders to a program, and you have to create a program. So that's what I will do now. So in the, where should I make it, in the init, or I will make another functions for that, void, and I will call init shader. So load init shader, okay, the init shader is good. So init shader, and it will wait two parameter, which is the name of the shader. So const char vertex shader and const char fragment shader, that's right. So it's a file name, so it will know which file to load. Of course, now I just have two shader. Maybe later on we have to expand this function a little bit, so we have other shader possibilities to load. But for now, this two will be enough. So in here I will make an std string and str, or source, let's call it source in here as well. So first of all, let's load the shader. So I will use the load file function, load file, and the first parameter is the actually this is a capital F. Okay, the vertex shader, that's the name of this shader. Actually, call it something vertex name and fragment name, because I want to use the vs and ss named variable as the identifier. So we load the file into the source. So we name. Right, so it will load the file into the source. So now we can use the load shader function. And this load shader function, if you remember, return an unsigned integer, and I have to store these IDs somewhere. For the sake of simplicity, I will go with the global namespace. Obviously, in a bigger project, you shouldn't use global namespace, but this is for the simplicity. So unsigned integer, and I will call VS and FS. So vertex shader and fragment shader. So the vertex shader will be equal to the load shader. It's waiting for the source, which we have loaded with the load file, and it's waiting for the mode. So I just press GL vertex shader like that. So the GL vertex shader will tell OpenGL that this will be a vertex shader, obviously. Right. Now the next thing is to actually make the source equal to empty, so source equal to empty, and let's load the fragment shader. So fragment shader equals to, first of all, let's load the file. So load file. I will load the f name, which is the fragment shader file name, and next do the source as well. So source, and I will do the same thing. So the fragment shader equals to load shader, and I get the source and the GL fragment shader. By the way, the fragment is basically a pixel. There are a very minor difference between fragment and shader, and the difference is that fragment will not necessarily get into a pixel. It has go on the masking operations, like for example the depth testing as well. So we calculate the fragment, but then if there is something closer to, for example, to the viewer, then it will not show that fragment. So that is the difference between fragment and shader, but you can pretty much use it interchangeably. Right, so we have loaded the two shaders, and now the trick is to create a program. The program is basically, if I go on with the C++ references, this is like a project. You can have different shaders, and you can apply different shaders to different models. For example, one model with one shader, another model with another shader, so on. But actually I will go on with just one shader, one program right now. So I will create an ID right here. This will be an unsigned integer as well. This will be the program's ID. So the program is equal to GL create program. This will create a program. It doesn't wait any parameter, and as I said, it's like creating an empty project in an IDE. Now you have to add the files to it. So basically you just attach the vertex shader and the fragment shader to this program, which is, as I said, it's like adding the files to the actual project in the C++. So if I go with the C++ reference, I hope I will not confuse you with this lot of C++ reference, but that's basically how you would create a C++ program, right? First of all, create a new file, then write down the source code. So create an empty file, write down the source code, compile it, get the error messages and fix them, obviously. Then later on create a project, for example, although you should create a project first, and add these files. So I will use the GL attach shader, right? Shader, and attach the vertex shader, actually first the program, and assign this vertex shader to the program. I will do the same, I will do the same with the fragment shader. So this is a duplicated call. Probably you could include, probably could create the program before the shaders, and then you would so you don't have to write two lines almost the same, but it doesn't really matter. Next is the linking operation. So if we go with the C++ reference, this is exactly the same as linking in C++. So we have a bunch of files, all of them compiled, so we will link together to one single program. To do that, I use the GL link program, and I will just give the ID of the program, which is program. Right, and the last thing to do is to actually use it. So if I go with the C++ reference, finally you are finished with the program. So let's start the executable. So GL use program. This will use the current the shader as this current program. Basically, the current program is the shader right now. So everything is rendered with this shader. And yeah, pretty much that's it. Now we have loaded the shaders. The VSFS are basically the vertex shader, fragment shader, and the program. But now we have to free the reserved memory. To do that, I will make another function. I will call it clean, and this clean function will wait no pointer, and actually it will just delete the shader. So we will release the reserved memory. To do that, I will use the GL detach shader to first detach the shader from the program. So I will detach from the program the vertex shader, and similarly I will detach the fragment shader as well. So basically I will do whatever I did here, just in the opposite way. So I delete it. Now I have to delete it, so I go back one and delete the create shader. So basically the opposite operation of the shader is basically the GL delete shader operation, and I will delete the VS, and similarly I will delete the FS as well. And finally, if we are here, we delete the program itself. So GL delete program. That's why we have to make the variable to global. Right, so now we are almost finished. We have to just call these this function which we have just wrote. So I call the init shader function, and it's weight 2 parameter, which is the two file names, so vertex.vs, and the next is the fragment.frag. This is the two file. I have created it into the same folder, as you can see. Now we have loaded it, so let's call the clean function at the end. So clean, and right, we are completely finished with the C++ program. So let's try to compile it, not run it yet since we haven't created the shader, but oops, there is a problem right here, and the problem is that I compile all of the C++ files, but I do not compile the C files, which is, as you can see, the extension is C in this case, gli.c. If you are using some IDE, probably it will not be a problem for you, but I just write gli.c right here, and now if I compile it, it compiled. If you probably try to run it, you will get an error message that it cannot compile and probably still uses the fixed functionality. So now it's time to create the actual vertex shader. So the vertex shader processes all of the vertices. Before I actually go on to programming, because we need some matrix operation, let me show you some survival kit for the matrices I have created in GIMP. Okay, so I just started up GIMP, and here is a matrix, actually not just one matrix, but here are two matrices. So a matrix is basically a bunch of numbers. So as you can see, this is a matrix. So 1, 2, 3, and 4, 5, 6, and 7, 8, 9. This is called a matrix. So so it's basically just a bunch of vectors, or we could say that the vector is a matrix which has either one column or one row. Obviously, the column is this and the row is this. So in OpenGL and GLSL, we usually have to multiply matrices by other matrices or vectors, but although I said that the vector is like a matrix which has one row or one column. So in order to get the multiplication between two vectors, I just show you quickly. Probably you can skip this section if you really want to, because we will not use too much matrix operation. I will just use one matrix multiplication with a vector. But anyway, if you want to know how does it work in the background, you can probably learn something in here or not, depending on whether how much you know already about matrices. So in order to get this value right here, this is this will result a 3 by 3 matrix. By the way, this is an n times n matrix, and this has to be an m times p matrix, for example, and the result will be an n times p, if you can follow me. So you can only multiply matrices if the number of columns in the first matrix is equal to the number of rows in the second matrix, as you can multiply. It's undefined. It's same as dividing by 0. It's just simple, not defined. So the first has to be n times m matrix, and the second will be m times p matrix. Then the result matrix will be n times p matrix, like that. So this is how does it work. But anyway, so this is not important right now. Let's make a multiplication. So how does the operation actually happen? So in order to multiply it, you get the, oops, I'm in a bad layer. Right, so now you get multiply 1 by 1, which is just 1. Add them to multiply 2 by 4, which is 8, and that 1 is 9. And then multiply 3 by 7, which is 21, if I am correct, I know correctly. And if you add these all numbers together, I believe you get 30 or something, somewhere in that range. To get the first row second number in the result, you multiply 1 by 2, 2 by 5, 3 by 8, and add them together to get this number right here. You do the same operation: 1 times 3, 2 times 6, and 3 times 9. If you want to get this number, so the last row, last column number, you multiply 7 by 3, 8 by 6, and 9 by 9, and add these together. And if you do these operations, you get a matrix, which will be the result of this multiplication. So let's take a look why it is important. And probably I should mention this, that matrix multiplication is not commutative. It's meaning that although in case of numbers 3 times 4 is the same as 4 times 3, in case of matrices you cannot just change the order. Although you can in special cases, but you cannot necessarily can change the you get it. So it may result in undefined if you change, or just simple bad number. So here I just calculated quickly the numbers. I quickly go to the next frame since you will check this, and I just calculated in head, so probably none of these actually are correct. So for some of these, as I know my math knowledge in the head, whenever I do it in my head. So we have a special matrix called identity matrix, which we have loaded with GL load identity function, and this is a matrix which has ones in the main diagonal and zeros everywhere else. And if you multiply any matrix with this, of course if it can be multiplied, because I said that it cannot be always multiplied, then you get back the original result. You can check it. So 1 times 1 is 1, 2 times 0 is 0, 3 times 0 is 0, so get 1. Or here 0 times 7 is 0, 0 times 8 is 0, and 9 times 1 is 9, so you get 1. So this is the identity matrix, and you will get always back the same result. And we use the GL load identity to load this in this matrix. So why are the matrices are important? Here are the important part. So I just drawn a triangle with these coordinates, which I wrote right down here: 0, 3, -2, -2, and 2, -2. And let's actually multiply these numbers with a matrix. So let's first of all try the identity matrix, so which has the main diagonal 1s and everywhere else 0. As you can see, we get back the same coordinates, so nothing changed. Doesn't seem too important. The next thing is actually try to get another kind of matrix. This is the 2, 2, 0, 0. So basically I just should draw lines here. So if I do the multiplication between these two, I will get 0, 6 as the result. So if I actually do this for every single vertex and I put it into here, as you can see, we double the size of this triangle. So this is basically the GL scale as what it does basically with matrices. So yes, GL scale as you can see. So of course, if it has a 2, 1, then in the x direction it gets 2, but in the y direction it becomes the same. So it will be something like this. Yeah, this. Of course, a little bit more lines and not curve like I did. Okay, so here we go, and then try another matrix. This is the 1, 0 and 0, -1 matrix. Let's see what it does. So if I do the matrix multiplication, you can do it yourself, you will see that the original triangle has been rotated 90 degrees. With a special cosine and sine values right into here, you can actually make any arbitrary rotation like 30 degrees or something, but I just show you a quick example of rotating 90 degrees. Right, so the last operation which we haven't covered, and basically this is the GL rotate as I write here. The last operation which was not covered yet is the translation. You can do translation with 2x2 matrices with 2-dimensional vectors. You have to use 3x3 matrices in 2-dimensional vector and 4x4 matrices in 3-dimensional vectors, vertices or vectors. It can be used interchangeably in that case. So that explains why GLSL and OpenGL use actually 4-dimensional vectors and 4-dimensional matrices. Right, so here is a simple example. I just write it a 3-dimensional vector, and every coordinate I will represent like the xy coordinate and just the one. This is equal to the w coordinate in the OpenGL. Probably you have already seen that there are x, y, and w, x, y, z, and w coordinate in OpenGL. And I haven't really covered the w coordinate since you don't really have to care about w coordinate ever. This should be just one always, although you can change it with a GL vertex 4f, for example, but you shouldn't. So here the last parameter is just 1. So if I do the matrix multiplication with the 0, 3, 1 vector, which is this right here, I will get 2, 4, 1 vector. And of course I should mention here that in the lowest row, so the last row, I actually write 2, 1 here. That basically means that I will use 2 as the x-coordinate translation and 1 as a y-coordinate translation. Similarly, if I do the other multiplication, here is the result. And after I did all of this, if I now put it into here at this triangle, as you can see, it has been moved 2 units on the right, so in the x direction, and 1 unit to up. So this is basically how the matrices work. I'm not sure if it will be really important, but at least help you to imagine that actually multiplying a vertex value with matrix actually does something. So I hope that you get from this. So, in the vertex shader, we have to create a main function, similarly as in C programs. Although, unlike in C programs, the main function is a return with a void, and it doesn't have any command line arguments, obviously. Why will it have command line arguments? It's run on the video card. So, void and main and empty parentheses. And similarly, then in any C language, we use the curly brackets to start the blocks. Similarly, then in any C language. So, I will not tell you that because you obviously know that. So the vertex shader most important result should be a position, GL underscore position with capital P, and GL underscore is basically the building things in GLSL, GL underscore with not capital GL. And yeah, these are building things, so I will not really cover that, but GL position is basically the vertex's position after we did the rotation, translation, and scaling, and the projection. To do that, we have to multiply the vertex, which is GL vertex. This vertex is basically the same as in the OpenGL program right here, this vertex right here, except that it has filled in the fourth coordinate with a 1, so the W. We don't really care about that. And yes, this is the vertex, and we have a matrix, obviously. So GL underscore model view projection matrix. This is the name of the matrix. This is the model view and the projection matrix we have created in the init function. Right here we created the projection matrix. This is the matrix which projects, so which use the perspective and create that shape. How does it called? Never mind. So create that shape, and the model view matrix which contains the rotation, translation, and scaling. So if you multiply the current vertex with this matrix, then you will get the new position, and this is a built-in variable. This should produce by the vertex shader. I could pass just the GL vertex into here, and that would pretty much mean that we don't care about translation, rotation, and scaling, and actually nothing we care about, but we care about, so I will do the multiplication GL underscore vertex. So the model view projection matrix is just a matrix which contains the model view, which is the transformations which we did, rotation, scaling, and translation, and projection is basically just whatever we created with the GLU perspective. So this will result the position. There is an alternative, and this is called F transform, if I remember correctly. F transform, like that. This is not E transform, similar to that. I'm not sure. I'm not really used to use this function, but basically it does the same thing. So I will just go back to the original, and basically that's the resulted the position. I will talk about these built-in variables later on, but for now, basically just the vertex shader most important task is to create the position of the vertexes, and pretty much for now this will be our vertex shader. So let's go back to the fragment shader and let's make one. So void, and similarly it has a main. The vertex shader and the fragment shaders have to have one main. So you can use more files, but have to have one main. Similarly as in C++ programs, you have just one main function. Okay, the fragment shader's most important function is to actually give back the color which the given pixel should be. So this built-in variable is called GLFragColor. The GLFragColor is the color of the current fragment, or as I said, it could be interchangeably used with pixel. So GLFragColor, and it is equal to a vector for the object. So we haven't created this object. This is built into GLSL. There are several built-in data types, and I will cover the data types in the next tutorial, since this is just a hello world tutorial. But there is one kind of built-in type which is called vec4. This is a vector 4, so it's a 4-dimensional vector, similar than we did with the vector 3D object in the FPS game, except this is 4-dimensional. Okay, so here we should give the color. Obviously later on we will do the lighting calculations and all kind of complicated stuff and give back the color to the frag color. For now, let's make it red so we can see if it is actually working or not. So the first parameter is the R, then the G, B, and an alpha value. Okay, the alpha value should be 1, although GL blend is not enabled, so it doesn't really matter in this case. Right, and pretty much we are finished and ready to run this program. If everything goes well, we will see a red triangle. This obviously vertex shader will run 3 times, every single vertex in the screen. I defined 3 vertexes. And the fragment shader will run a lot of times because it will run every single visible pixel on the screen. So let's try to run it. We already compiled it, and as I said, because we are using files and we dynamically load in these files, we don't have to recompile, so I'm pretty sure we can run it. So run it. As you can see, the compile status is empty, and oops, there is something problem here. Okay. There is something wrong, because we should get a red triangle, not a white triangle, so we can see that it is not working and I screwed up somewhere. Oh, I think I know where did I screwed up. I forget to return with the ID right here in the load shader function, because as I said, it should return with the ID, so return ID. And now, if everything goes correctly, after I compile this program again and run it, we should get a red triangle. And that's right. Oops. Sorry about that. Yeah, here we go, a red triangle, the first hello world program for GLSL. So the fragment shader will run every pixel which you see red right here. Okay, and I'm pretty sure this should conclude this tutorial, because this is just the first tutorial. I don't want to go into too complicated things. So thank you for watching and have a great day.